Good afternoon, everyone. Welcome to ACSM Brown Bag and Science webinar. We're thrilled to have you with us for today's presentation from Dr. Christopher Black. We'll hear more about Dr. Black in just a minute, but first we want to tell you a little bit about the Brown Bag series. This year we're using the Brown Bag series to highlight various ACSM regional chapters. We'll start each Brown Bag with someone from the regional chapter. It could be a leader, a student, etc., telling us a bit about some of the activities of the chapter. Then the presentation will be from a member of the chapter. Today's presenter is a member of the Central States chapter. A few housekeeping items. Our presenter will give us a 25 to 30-minute talk, followed by Q&A. Please type your questions into the question area on the GoToWebinar screen, and we will take as many questions as possible after Dr. Black's talk. If you have trouble hearing or seeing the presentation, it is likely due to your internet connection. So go ahead and log off and then log back into the webinar. We will record the presentation, and within about a week, we will send you the link to the recorded version. So again, thank you for joining us today. I will now turn it over to Dr. Matt Ganio. He's from the University of Arkansas and is the chapter president for the ACSM Central States chapter. He's going to tell us a bit about the chapter and then introduce us to Dr. Black.
Well, hello. Thank you and welcome to ACSM's Brown Bag and Science talk titled Afferent Signaling and Endurance Exercise Performance, Friend or Foe. I want to thank National ACSM for organizing this and allowing us to co-host. Central States chapter represents Arkansas, Kansas, Missouri, and Oklahoma. Since 1975, the chapter has worked as the grassroots organization aimed to enhance the experience for students and professionals in the region. We pride ourselves on providing outstanding opportunities for our students by way of professional development and at our conference each year. We support them through a variety of mechanisms, including our student research grants. We're also proud of our outstanding faculty that do impactful research and teaching in the region, and a good example of that is Dr. Chris Black. Dr. Black is an associate professor in the Department of Health and Exercise Science at the University of Oklahoma. He graduated from Hendrix College in Conway, Arkansas with a BA in biology in 2000 and received both his master's and PhD in exercise physiology from the University of Georgia, which I had the honor of overlapping with him there, and so we are commonly cheering for the Bulldogs this weekend as they beat Florida. Chris was a postdoc fellow at UGA from 2007 to 2008. His primary research interests are in the area of neuromuscular physiology and the causes and performance consequences of exercise-related musculoskeletal pain. Specifically, he examines the effects of daily physical activity on acute and chronic changes in endogenous pain inhibitory function, as well as the impact of pain, muscle damage, and a host of other supplements such as caffeine and carbohydrate mouth-rinsing on neuromuscular function. So I want to welcome Dr. Chris Black and appreciate everyone's attention today. And Dr. Black, the floor is yours.
Thank you, Matt. And I want to thank National ACSM for providing us this opportunity to present a little bit of our research that my students and I have worked on over the years. And I hope that it will be of interest to everyone. So as I was sort of unfortunate to figure out, I think it was yesterday, if no one has been paying attention to anything but the election, we had a giant ice storm in Oklahoma. It was last week, and I've been without power for 11 days now, and I missed the fact that in the exercise and sports science reviews that there was a really nice review article by Marcus Amann on a very, very similar topic to what I'm going to talk about today. So I'd really encourage everyone, I'm going to show a little bit of data from Marcus later on today, but I would really encourage everyone to go in and give this a look if the things that I talk about today are of interest to you. So I will try to do this, and I love talking about exercise and performance. And so I thought a good place for us to start today and to kind of contextualize some of the research that we do in my lab is to talk about endurance performance. And so if we think about Eliud Kipchoge and his attempts to break the 2-hour marathon, I want everyone to kind of draw your attention to the fact that when you run 1 hour, 59 minutes, and 40 seconds, which is about a 4:34-mile pace, which, if I remember Dr. Ganio correctly, is just a little bit faster than what he could do when we were at UGA, but not much. If you want to run that fast to try to break the 2-hour marathon, if you are off by merely a second a mile, then you're not going to make your under 2-hour thing. And so when people think about the things that determine exercise performance, many of you probably think of the very traditional physiological things like VO2 max, lactate threshold, critical running velocity, which we'll talk a little bit about later, movement economy, or running economy. The thing you may not think about, though, is something called afferent signaling. And that's what I want us to talk a little bit about today. And so I think before we launch into any of our research, it's probably worth giving a little bit of background on what afferent signaling is. And this is by no means going to be a completely exhaustive kind of examination of this. So type 3 and type 4 afferents are going to be thinly myelinated or unmyelinated free nerve endings that are going to be in and around skeletal muscle and capillaries and blood vessels in a host of tissues. Okay, they're going to tend to respond to a host of chemical and mechanical stimuli, things like mechanical pressure from force production, declines in pH, bradykinin, potassium, hot, cold, pretty much any sort of stimuli you can think of. You're going to have afferents that will respond to them. They're important during exercise for a couple of reasons. One, they're going to be one of the places where we can signal and try to make sure that we are matching the blood supply to demand in working skeletal muscles. So if you have localized ischemia or localized changes in metabolism and changes in the biochemical environment, then the 3 and 4 afferents are hopefully going to drive changes in cardiovascular control and pulmonary function in an effort to match supply and demand. So it's delivering enough oxygen and nutrients to working skeletal muscle. One of the other things that they do that's going to be more of our focus today is going to be they provide sensory information, things like proprioception or sense of position, as well as information about discomfort and muscle pain during exercise. So this is a really nice figure from the Aman review that has just come out, and this is going to be this area of where I want to talk about things. Is afferent signaling your friend, or is it your foe if you are out and trying to do a bout of endurance exercise? And so we'll start off on the friend side here, on the Captain America side. And so you can imagine that you're out and you're riding your bike and you're cycling, and as you're going to increase your exercise intensity, you're going to stimulate these 3 and 4 afferents, and those are going to drive those changes in cardiopulmonary responses and try to match oxygen delivery in an effort to limit peripheral fatigue. Right, we want to make sure we have enough oxygen to our working muscles so that we're not going to get peripheral fatigue. If that doesn't happen, then that can be bad. So this kind of matching is going to be kind of on the friend side. Now, on the foe side is that the same afferents may also, or different afferents, but may respond to things like intramuscular pressure, changes in pH, the accumulation of bradykinin and adenosine, and that may result in pain or some other sort of sensation that may then signal back and limit descending drive from the motor cortex to the motor neurons and limit force production. So this would be central fatigue. So there's this interaction here that we want to change cardiopulmonary responses to limit peripheral fatigue, but the things, while we're getting that may be good, we may also be getting central fatigue. And so what I'm very interested in, and what our lab tends to be very interested in, is, well, what if the 3 and 4 afferent signals are going to result in pain? And then how might that pain sort of lead to this output from our motor neurons, and how might that have an impact either positively or negatively on exercise performance? So very quickly, just a little bit of background about pain and how we sense pain. I want to remind everyone that the sense of pain is a perception. And the specific afferent receptors that we are going to talk about today are called nociceptors. And you have nociceptors that are going to be sensitive to a host of different stimuli. The ones that are really important for exercise are going to tend to be these A delta fibers that are going to be sensitive to intramuscular pressure. So as force production goes up, intramuscular pressure goes up, that can stimulate these A delta fibers. And then they're also going to be C fibers or type 4 afferent fibers that are going to be sensitive to increases in body temperature, increases in metabolic byproducts like hydrogen ions and adenosine. See, all of these are going to sense these, signal through the dorsal horn of the spinal cord up to the brain, where they're going to be interpreted potentially as being painful. Okay, so if we were interested in the influence of pain on exercise performance, one of the things that we need to be able to do to experimentally try to examine this is we need a way to manipulate pain during exercise. And so what I'm showing here is I have some data from a couple of studies done out of Pat O'Connor's lab, where I did my postdoc at the University of Georgia. And so in the left panel here, we have percentage of maximal power output on the x-axis and a rating of pain intensity from 0 to 10 on the y-axis. And so this is just pain ratings during a cycling VO2 max test or a cycling VO2 peak test. And it was done in the presence of a placebo or in the presence of consuming aspirin. And so they were attempting to see if we gave you a non-steroidal anti-inflammatory, does that alter the pain you experience during exercise? And you will note this kind of positively accelerating increase in pain, but no difference with aspirin. So aspirin doesn't work particularly well for exercise-related pain, but caffeine does. And so here are some additional data. And rather than examine this during a VO2 max test, this is going to be 30 minutes of cycling at roughly 60% of VO2 peak. And so they gave a 5 milligram per kilogram body weight dose of caffeine or a 10 milligram per kilogram body weight dose of caffeine. And what you can see is that our rating of pain intensity in the placebo condition is here, and then in both caffeine conditions, we can get a significant reduction in pain during exercise. And this caffeine effect has been replicated on multiple occasions. So how does caffeine function? Caffeine is an adenosine receptor antagonist. And so when we're going to get heightened ATP turnover during exercise and exercise of increasing intensities, what is going to happen then is, as it gets metabolized out to adenosine, then caffeine is going to competitively inhibit various adenosine receptors in the periphery and in the central nervous system, and that's going to prevent the adenosine from having its stimulatory effects and evoking pain. So to that end, I wanted to talk a little bit about a couple of studies we have done with caffeine today. And so the first of which was a labor of love across several of my faculty stops. But what we did was we took 14 participants. They were low caffeine consumers, and we conducted a randomized double-blind placebo-controlled crossover experiment. And we gave them a 5 milligram per kilogram body weight dose of caffeine. And so what we were primarily interested in was if we can manipulate pain, and also potentially with caffeine, if we can manipulate central fatigue or motor unit recruitment, can we demonstrate some sort of a change in performance during cycling exercise? So the protocol that we had them do, following several familiarization sessions, we had 4 experimental conditions. Where we would have our individuals ingest the caffeine or placebo. They would rest for 60 minutes. We would perform some maximal voluntary contractions with the twitch interpolation or electrical stimulation applied to determine their strength and their ability to recruit their motor units. We then had them cycle for 30 minutes at 60% of VO2 peak, either riding the bike in a traditional way using their legs, or riding the bike doing arm crank cycling, using their arms like this. And so they had a placebo and a caffeine condition with each one of these. Now we'll talk a little bit more about kind of why we did that in just a minute. Immediately following this 30-minute bout, they did a 10-minute time trial, and they had to cover as much distance as they could during 10 minutes. And that was going to be one of our criterion measures of, was the caffeine going to be ergogenic? And so I don't want to bury the lead on this, although it was maybe not, to me, the most interesting finding. What we did find, like many other people have, was that caffeine ingestion improved their 10-minute time trial performance. And so about a 5% increase in the legs, so doing traditional leg cycling. This doesn't seem like a particularly large amount, but I can assure you that 5% is a significant increase when you're worried about gaining 2 or 3 or 4 or 5 seconds on someone in a race. Interestingly, during arm crank cycling, we did not see a statistically significant increase. The caffeine worked in legs, but not in the arms. We think that's related to motor unit recruitment. We'll come back to that in just a minute. That's a limitation of our design. So when we look at pain, I want to draw your attention to that we measured pain every 5 minutes during the leg cycling and arm cycling. So we have exercise time here on the x-axis, and we have our measure of muscle pain on the y. And so you can see during leg cycling, after about 15 minutes or so, we're seeing a significant reduction in pain, relatively similar responses in the arms. So from a pain perspective, we are seeing similar reductions in pain during both arm and leg cycling at a relatively similar exercise intensity. However, when you look at this, when we look at the pain response during the 10-minute time trial, things become a little bit more interesting. And so here we have pain measured at the end of every minute during the 10-minute time trial. So we have time here on the x-axis in both panels, and we have our measure of muscle pain here on the y. And so what I want everyone to note with this is that there was not a difference in pain or in the perception of pain during the placebo or the caffeine trials. And so if you look, they almost completely lay right over the top of each other. And you can see as well that pain is getting to be very, very severe out here towards the end of exercise in both arm and leg cycling. So in this one, especially in the legs, we've got no differences in pain, but we have a significant improvement in exercise performance. And so one of the things that we were curious about from all of this is it made us wonder, were people pacing their exercise based upon their perception of pain? And there's a huge, huge amount of research that has been done on pacing strategies and what it is that people will do to pace themselves during exercise. We wondered from all of this, could they simply be kind of estimating how much pain they were under and then using that to judge how hard they could go to make sure they could cover their full amount in 10 minutes. And so when we look in the literature, we thought that seemed plausible. When you look in the literature, there's actually a little bit of additional evidence from all of this. There's some data from Alexis Malgar, who you're going to see some stuff from his students in a little bit later. But they were showing, they gave acetaminophen. So if you gave people Tylenol, they saw almost exactly the same thing, that rather than a fixed time trial, they did a fixed distance. And so in an acetaminophen condition, it did not take them as long to complete the distance as it did with a placebo. And if you look at their measure or their estimate of pain over the course of their 16-kilometer time trial, they're laying right on top of each other. And so the take home for us from both of these things was, it looks like that it's very plausible that people are using this afferent feedback that's causing pain or causing this sensation of pain, and they're using that feedback to allow themselves to choose their exercise work output in order to try to maximize how much ground they can cover or how fast they can cover a given amount. And so the take home from all of this is, well, if we can give you something, manipulate your pain, make exercise less painful for you, then that might have this ergogenic effect, and you might be able to improve your exercise performance. So to further follow up on all of this, this is one of my former master's students. His name is Alex Gonglak. For his master's thesis, what Alex decided to do was we set out asking the question, what if we ask people specifically to pace their exercise intensity on pain, gave them caffeine in the hopes of manipulating that pain? Could we also then see a change or a corresponding change in exercise performance if we told them specifically to pace on pain? So very similar to our previous one, we had low caffeine consumers. We gave them a 5 milligram per kilogram dose of caffeine again. And we did a couple of trials. And I'm going to show you guys just data from this first study where we put them in a moderate pain condition, where they warmed up on the bike for 5 minutes. We had a transition period where they increased their intensity. And then we gave them a chance in this couple of minute period to ramp their intensity up so that they could then get to a pain rating of a 3 out of 10. Participants in this were blinded to their power output. So we covered up the power output thing on the bike. They were then able to adjust their power output whenever they wanted to, but the take home was they always had to be at a pain rating of 3, okay? And so when we did all of this, we then were going to cover, they had, I believe it was 15 minutes that they were cycling at that particular intensity. And we wanted to see how much distance they covered in that time period. So when we look at this, we were essentially clamping their pain at a 3 out of 10. And what we found was that they covered more distance per pain rating and per RPE. Their RPE and their pain were both relatively constant across the whole thing. But what we found was that the distance covered across that 15-minute time was greater in the caffeine condition. So between placebo and caffeine, pain is exactly equal, okay? They're specifically pacing on that, but they're covering more ground. So if we look at it, the distance covered per kind of time period where this really begins to become more apparent is out as exercise begins to progress out over time. And so from all of this, we are again drawing the conclusion that we don't have particularly direct evidence from our other study that people were in fact pacing based upon pain, but we do have evidence from this study that if you use this afferent feedback that causes pain, if we specifically ask you to pace based upon pain, and then we give you something that can potentially manipulate that pain, then that does actually manipulate exercise performance. And so further evidence showing that that kind of afferent feedback may in some ways be integrated and playing some role in your exercise performance. So based upon kind of what I've shown you guys now, let's take a little accounting of where we are. Is afferent feedback a friend or a foe? So what we see is that if we can ingest an analgesic drug, we may be able to improve your exercise performance. We are assuming that analgesic drug is blunting some of the afferent feedback, blunting some of the pain perceptions, and then it's going to potentially improve performance. So in that way, we may say that at least painful afferent feedback may be a foe. So we've got Thanos here. He may be your foe for exercise performance. So in that way, doing something to be in less pain may be beneficial. Okay, well, that's not the whole story. There's this other side of things, and there's some other kind of fascinating evidence that is out there. And I want to present a little bit of background on all of this, and then some emerging data that we have from our lab that one of my PhD students is currently working on. So another way to manipulate 3 and 4 afferent signaling, okay, is to induce a significant amount of peripheral fatigue. And so this is not necessarily going to be things that are going to be directly related to pain, but it may be peripheral fatigue. So it's a buildup of metabolites. So what I have here in the left panel, this is going to be data from a study from Marcus Amon, and I apologize to him, I've spelled his name wrong here. That is my bad, I at least have it correctly over here. And what you're seeing is this is a 5-kilometer time trial. And participants performed 3 different conditions. And what you have here in the top panel is going to be an integrated EMG signal from their quadriceps while they're cycling. And then power output on the bike here is going to be shown in panel B. Okay. And so the 3 conditions are going to be, they have a control condition, okay, where they just perform the 5-minute or the 5-kilometer time trial. They then have 2 separate conditions where they did a pre-fatiguing protocol. And so they cycled before they did this 5-kilometer time trial at sort of a relatively high intensity for a little while or a relatively moderate intensity for a while. And in doing so, then they're inducing different amounts, so they're manipulating the amount of peripheral fatigue. So what you can see here in the dark circles is the high pre-fatigue protocol. Here in the triangles is going to be the control, and then our open circles is going to be the kind of moderate pre-fatigue protocol. And what you will note is that during the high fatigue protocol, high pre-fatigue, you have this marked reduction in power output. And so if we have lots of initial afferent signaling, then that seems to have an inhibitory effect on our power output. And that appears to be that this induced peripheral fatigue is resulting in further central fatigue or decreased motor drive to the muscles that's going to correspond to this decrease in power output. So here we have a afferent input that may not necessarily be painful, but is going to be there and is going to result from peripheral fatigue having some inhibitory effects on central motor output. Okay. So some future stuff that they have done, which I think is really, really fascinating, is here is what is essentially the same experimental setup. Okay, we've got 3 cycling conditions, again, 5-kilometer time trials, but in this one, rather than enhancing afferent signaling, they have chosen to blunt or almost entirely inhibit afferent signaling. And so in this, we have three conditions. We have a control condition here in our closed triangles. We have a placebo condition in the open circles, and then we have a fentanyl injection or intrathecal fentanyl injected into the spinal cord in the lumbar region here in the open triangles. So with the fentanyl injection, you're going to completely blunt, or completely is the wrong word, probably somewhere between 50 and 60% reduction in afferent signaling from that peripheral fatigue back into the central nervous system. And so what I want you guys to pay attention to is look at the power output and how it changes and is different. You get this very different profile when we blunt afferent feedback. Early on, they get this increase in power output over our other kind of control conditions. They go out really, really hard because they get no feedback from those afferent sensations. And then they're going to give out and have this reduction, this lowered power output on the back end of their time trial. And they're going to end up doing a little bit worse here. So having that afferent feedback does not allow them to integrate in some ways and properly pace based upon the peripheral fatigue that they're adjusting to. And so from this, we're going to begin to say, okay, well, yes, maybe again, there's evidence that afferent feedback is a foe and is not good for our performance because it may inhibit central output. But we may need some, because if we have a reduction, we can't sense that feedback, then that may also then impair exercise performance, which I think is really, really fascinating. So very, very quickly, before I show you guys a little bit of data from our lab that we have, I want to very quickly mention this idea of something called critical power or critical velocity or critical torque. So this is something that was observed by A.V. Hill in the 20s. It was another thing that was proposed in the 60s. And essentially what critical power or critical velocity or critical torque represents is this is a power output or a running velocity at which you can almost entirely supply all of your AT production through aerobic metabolic pathways. And so right at critical power or right at critical velocity, you can maintain a steady state of aerobic metabolism. If you tip just slightly over critical power or slightly over critical velocity, then fatigue is going to occur and you're going to essentially end up fatiguing out and going to max, okay? And so this is going to represent the cycling power or the running velocity that if you were wanting to try your Kipchoge and you're wanting to try to hit your 4:34 mark, you want to make sure that your critical running velocity is able to allow you to go that fast. So this is one of the best indicators of endurance exercise performance from a race standpoint. People that have a higher critical power or a higher critical velocity are going to potentially be better racers. So to take all of this into consideration, we wanted to apply some of our afferent feedback things into how might that affect critical velocity or critical torque for us. And I'll show you guys a little bit about our experimental setup here. So this was the brainchild of one of my former master's students, Natalie Jansen, who is getting her PhD in John Howley's lab in Australia right now, and one of my current PhD students, Robbie Height. And so what they decided to do was we were going to do knee extension exercise, and we were going to have individuals hold 20% of MVC until task failure with their non-dominant knee extensor. So they would have a person that would kick like so. We then put a blood pressure tourniquet up here, and we had them go to task failure, and then we inflated this blood pressure cuff and occluded blood flow to that non-dominant leg. We then had them immediately switch over, and they performed a critical torque test where they were doing 5 minutes of maximal knee extension contractions with their dominant knee extensors. And so in doing this, then they're doing repeated MVCs, a 3-second contraction followed by a 2-second rest period. And they did that for 5 minutes. And I'll show you guys the pattern of what happens to force. But they had a condition where they had either no occlusion and no pre-fatigue on one leg, or lots of pre-fatigue. And so we were having heightened afferent signaling or kind of normal afferent signaling. And so what we found when we look at all of this is you guys are seeing time here on the x-axis and MVC values, or so peak isometric torque. And what I want you guys to look at is, as you will note over the course of 5 minutes, that there is fatigue that develops and your MVC begins to fall until it plateaus out here in the back half of the last couple of minutes of our 5-minute test. And so what you can see then is we're going to have our dark circles are the control condition, so normal afferent feedback. The open circles are the occluded condition, so we have heightened afferent feedback. And we undertook our critical torque test. And the first take home is that if we look out here at what torque does it plateau, there's no difference between our conditions. So heightened afferent feedback does not seem to alter critical torque. But we do begin to see some changes, and these are some significant reductions in torque here in the first, say, 30 to 45 seconds or so. This looks like it may be a pacing strategy in some ways, that our individuals thought they were trying as hard as they could, but they may have had, and this is going to correspond to a reduction in motor unit recruitment. We don't quite have all of those data ready for prime time to show you guys this, but we look at this and think, at least in our hands, heightened afferent signaling is not necessarily going to affect that critical velocity, or what could be that critical torque or critical velocity from a race standpoint. So if it's having some effect, it may be on pain and that pain on motor output, but not necessarily on this particular parameter. So is there a little bit of other evidence that is out there on the potential impact of pain and afferent signaling? There's some really fascinating data that have recently come out. One study out of Alexis Mager's lab from one of his students at the University of Kent, and then some other data that we have here that was just presented, I think, earlier last week at the European College of Sports Sciences presentations. But you can see in these data, they've injected hypertonic saline into the quadriceps. So they've injected saline solution. It hurts when you get saline solution injected. And what you will note then here in this one is that here's the percentage of exercise time on the x-axis, pain intensity on the y. This is the hypertonic saline condition. And so exercise is more painful, okay? And then if you look at how long they were able to actually hold this isometric contraction, this is the hypertonic saline condition. And they had a reduced time at which they could hold this isometric contraction compared to either a placebo injection or no injection whatsoever. So in this instance here, we have heightened pain, reduced performance. Again, looks a lot like our caffeine data and the acetaminophen data. And then here we have these Norbury data that are going to be here where they find something that is relatively similar, okay? Again, heightened pain during, with the hypertonic saline injection, heightened pain during exercise, and a reduction in the time to task failure. So these kind of things are going to look relatively similar. I'm really looking forward to these data getting published. Dr. Norbury was nice enough to send me some of the data to look at. They have some transcutaneous magnetic stimulation data. They've done a lot of really fascinating stuff to see how this might be affecting either cortical excitability or motor neuron excitability, and try to tease out exactly where this heightened afferent signaling is having an effect. So I would encourage everyone to be on the lookout for all of these things, because they're really fascinating data there. Okay, so here we are at the very end, just to wrap up. Afferent signaling, friend or foe? And I'm going to sort of hedge my bets here and come down on the idea that it may be a little bit of both, okay? That you exercise your muscles, you're going to get this buildup of metabolites out in the periphery, a little bit of peripheral fatigue is going to occur. Those signals are going to be sent by our afferents back to the brain where they may be interpreted as pain. There may be also some other kind of peripheral afferent stimulation that it may not be painful, but between pain and this other stimulation, there may be some feedback then at the level of the motor cortex or above the level of the motor cortex, integrated in the at the level of motor neurons. And some of this may be good if we can reduce pain, and that may help us from a motor cortex standpoint to continue to drive the muscles, to continue to motivate you to drive those things. But also, we know that if we block some of this afferent signaling, that may also be deleterious. That if you block all of it or a large portion of it, then you may not properly be able to kind of manage the amount of peripheral fatigue that you're experiencing, and therefore it may lead actually to more fatigue and worse performance. Okay, so quick thanks here at the very, very end. I just want to thank a host of the students that have worked on some of these projects through my laboratory, especially Alex Gonglak, who is now getting his MD at Temple, to Natalie Jansen and Robbie Height, who were kind of the brainchild of some of these things. A big thanks. Some of my collaborators at University of Mississippi, Nicole Dabbs and Dwight Waddell, and then a couple of folks here at UGA who have now moved on to other things, Carl Otte and Jake Caldwell, and some funding sources from the universities where I have been. This is an old picture of our lab group. I always want to thank, especially kind of in our not having power and things here, thank my wife and my little daughter for everything. And with that, I will close and would be happy to try to answer any questions that people may have. Thank you.
Awesome. She looks like a budding scientist for sure.
So we are hopeful that she will at least be curious about some things.
Good deal. All right, so everybody, please enter your questions into the GoToWebinar question area so that we can, have lots of good discussion. I have a few questions to start us off. So, Chris, in the first study that you described, were the participants caffeine naive?
Yes, they were indeed caffeine naive. They were under 40 milligrams per kilogram of caffeine consumption a day. So basically, if they had any more than a 12-ounce can of soda a day, then, or about average of about that much, then they were not included.
Awesome. Okay, so how about, here's another question. Does pain tolerance or previous experience with pain seem to make a difference?
That's a really fascinating, really fascinating question. And we have a little bit of data that we are working on where we've tried to look at differences in pain sensitivity. We've got a couple of studies that we've published on differences in pain sensitivity between athletes and non-athletes. And at least at baseline, like not during exercise, but just their sensitivity at baseline does not really seem to be particularly different. Now, during exercise, if you match them on kind of percentage or kind of relative intensity, we don't tend to find them to be that different in their reporting of pain. There is some older data that maybe athletes may tolerate any amount of pain a little bit more so, but that's not widely studied. And so I think it's a really fascinating question that is out there, because if you were to try to pin me down on an answer, I would say I bet there are some differences, but we're still trying to work out how to experimentally kind of check all of that.
All right, here's another question. So is there a mechanism that impairs performance at the later part of exercise when blocking afferent feedback?
So my guess is that the mechanism is going to be kind of normal things that contribute to peripheral fatigue. So the accumulation of hydrogen ions, right? Other kind of that, and blocking of excitation contraction coupling, the precipitating of inorganic phosphate binding into calcium inside the sarcoplasmic reticulum and preventing further release. So, and I would encourage everyone to go read some of the Aman papers. But my interpretation of their data and their explanations of those data are that what essentially happens is you block the afferent feedback. And so I don't know if anyone has ever had a nerve block, but I know a few of the folks in that lab that have participated and that have had the nerve block, and apparently you feel great. And so what happens is you just go out really, really hard during that bout of exercise, and because you're not able to get the afferent feedback that says we're accumulating a huge amount of metabolites, we're probably becoming more and more acidic out here in the periphery, there's lots of peripheral fatigue that is occurring, we need to slow down in order to modulate all of this. And not completely fatigue ourselves out, they get none of those signals. And so they go out way too hard, they accumulate a bunch of metabolites, they get lots of peripheral fatigue that kicks in, and that forces them to have to then slow down on the back end. Whereas if you have a normal amount of afferent feedback, you can more closely match and monitor some of that peripheral fatigue that is going to happen, which is what tends to happen if you look at a lot of the pacing strategy research. People go out kind of hard, and it's this sort of U-shaped thing where they go out hard, they slow down a little bit in the middle, and then everybody kicks at the end. And so monitoring that feedback allows you to kind of plateau in the middle and save some for the kick. Whereas if you get none of that signaling with the fentanyl, you've got nothing left to kick with at the end.
All right. What about, to what extent is perceived pain similar to RPE?
Oh boy, we could spend an entire week talking about all of that. So I think it's a really, really important question. And I would reference some people to a lot of the work of Samuel Marcora. There's some really fascinating work on what exactly is RPE, what are the afferent and other sort of signals that are going to go into RPE. So what we have found, and this, I'm going to say this is mostly anecdotally in our lab, is that if you have to be very, very specific, and this is always the case, but you have to be very specific about the instructions and the definitions that you give when you are defining RPE to people. You have to be very careful and very precise that they understand when you're telling them that I want you to differentiate between pain, how much does this hurt, and how effortful are you perceiving this amount of exercise to be. And so I think, and again, this is, we have some other data with things. I think that pain is one of the things that most people will integrate into their definition of RPE. If you look at all of our things, the RPE and the pain tend to track very closely. When we do something to inhibit pain, RPE tends to go down, right? When we do things that make pain go up, RPE also tends to go up. They are two distinct constructs, though. And so I think that's the kind of the key thing. And if you get your definitions wrong, then you may not be able to separate those.
All right.
I also think that in a lay person, if I was to take, sorry?
Oh, sorry, go ahead.
If I was to take a lay person, okay, if I was to take a lay person who doesn't know much about this, is not an exercise scientist, and you were just to ask them to go out and regulate kind of how they're gonna exercise based upon how they feel, I bet they do it more so on pain than on some sense of effort because they're much more familiar with pain. So we'll leave it at that.
All right, great, thank you. This is a little bit of a longer question, so bear with me as I read this. So the question says, there's a lot of evidence for large individual differences in pain, even in response to the same stimulus. Despite the main overall effect you described from your research, can you discuss if everyone responded the same or if there was meaningful individual differences in the pain or performance outcomes? Also, how much variation is there in afferent signals from day to day given an identical exercise stimulus?
Okay, so Lynette, the first part cut out. I'm guessing it was something about were there sort of different responses in the caffeine experiments from both the pain and from a perception and a performance standpoint, and then daily variation. I will answer the second question first. That I'm not familiar with what the day-to-day fluctuations in afferent signaling in response to kind of common stimuli might be. I think that's a really fascinating question. That may be something that we will be looking up this afternoon in my lab, is what are those day-to-day things. My guess is there's probably a little bit of fluctuation based upon some things, but I would not want to speculate on all of that. As far as were there individual differences in our participants in how they respond from both a pain and a performance standpoint in response to caffeine, then the answer is yes. People are responders and non-responders to caffeine. There's some interesting arguments about how we parse those people out. If you should just look at your responders or do kind of some separate responder, non-responder analysis and those kinds of things. We tend to find that there tends to be significantly more variation in the performance response than there is in the pain response. And so we tend to find that if you do some sort of submaximal exercise, that when you give people caffeine, almost everyone experiences a reduction in pain. And that's probably a bit of an oversimplification. There's probably some that don't, but it's much more consistent with pain than it is with the performance outcome. And so if you try to, correlate the delta in pain perception to a delta in the performance outcome, it does not always track as well as we would like. But that's also that I meant to mention this, is that using caffeine to manipulate pain, this is not as clean a model as maybe the hypertonic saline model is going to be, because caffeine is also going to stimulate the central nervous system, and caffeine can potentially improve motor unit recruitment. So you may or may not be getting reductions in pain, and you may or may not be getting improvements in motor unit recruitment. And so you may be kind of mixing things that could both influence the performance aspect. And that may partially be why we see more variation there.
Great, thank you. Here's a question about how different is pain from affective responses like pleasure, displeasure? Are those different constructs?
So that's again a really interesting question. So I think again it's going to depend upon kind of sort of what affective construct you're going to want to look at. So I think that this is where I think there's probably going to be some debate about all of this. You can make an argument that if you define pain very, very closely, very precisely as something that's going to hurt, then I think you may be able to separate pain from some other affective constructs. But then at the same time, if you look in the literature, there are also some people that they'll do this contralateral occlusion, or they'll do something like that, and they'll ask people how much that hurts, and they will use that pain response to try to estimate the total kind of affective response that people are getting. That the more painful it is, then the more metabolite buildup and things that there's going to be. And so I think it can get to be a little bit messy, and I think that there's probably a lot of opinions on all of that. And I don't know that this is really the place to have a really kind of precise discussion about that.
All right. So how about this one? The question is, what would be your recommendations to elite athletes to optimize their pacing strategies by utilizing afferent feedback?
So that's the really great question, right? So if anybody has watched the documentary on Breaking 2, what I found to be fascinating was, at least in the first attempt, they had a pace car, and the pace car shot a laser out in front of them, and the pace car drove at precisely the kind of correct pace that they wanted people to be at. And so if I'm remembering correctly, they were having them try to run at like a flat pace, like try to stay at the exact same pace the entire time, right? Which in some ways might be not a particularly great way to respond to your afferent feedback. So what I would try to argue with people about, or what I would maybe advise people to do, is within the kind of WADA legal limits, if you can consume something that might partially blunt some of the afferent feedback, caffeine, acetaminophen, something like that, in kind of this legal dosage amount, where you're going to get a little bit of a blunting, but not so much of a blunting like if you had fentanyl or something, where you can still get some of the proper amount of feedback of what what those things are going to be. Then that can help you in that middle section, in that kind of more kind of plateaued out bottom section as you're going along to respond. And then, if you feel good, maybe you can speed up just a little bit. If it doesn't hurt that much, you can speed up just a little bit, but not so much. This is where I'm gonna go 1 second faster or 2 seconds faster per mile or something, and see if I can capture a little bit of gains in that way. And then if I begin to feel a little bit more pain, then maybe I want to slow it down a second or two or something like that. That would be my suggestion in that way. But I think that's a really interesting. There's Samuel Marcora has a paper on the influence of sort of encouragement, and that during the second race, I believe, when Kipchoge actually broke it, I think there was they were on the course, there were actual fans that would cheer, and how that kind of feedback might actually be able to counteract some of the other kinds of things. There's some really interesting stuff with that. And in some ways, just as a side note, if you're interested in those elite things, there was a paper that it may have just came out yesterday from Andy Jones's lab with Annie Venetalo and some others, where they were looking at some of the physiological things, VO2 max, critical velocity, lactate thresholds, and things in a group of those runners that are attempting to break the 2-hour marathon. So they kind of look at the physiology, really cool stuff, really fascinating, really well done. So I guess I would say manipulate it a little bit if you can, and then listen to your body the rest of the time, and see if you can use that to kind of do your best.
Yeah, I think this is an interesting sort of follow-up question. I think there's always, for people who don't run or don't do marathons, there's always this, do people acknowledge and evaluate their pain, or do they just dissociate from it and try not to think about it? What do you know from the literature that's out there on the elite athletes?
So another really fascinating question. And so how athletes sort of may differ and may choose to attempt to deal with whatever pain they're experiencing, during exercise. If you are going to try to exercise kind of right at, or in some instances over, your critical running velocity or your critical power, as you accumulate this peripheral fatigue, it's going to be painful. It's going to be uncomfortable. And how people tolerate that, if they are able to kind of psychologically dissociate, I acknowledge the pain and I'm just going to keep going, right? Is if how well they're able to do that. I know I'm not very good at being able to do that, which may be why I was never an elite athlete. I'm sure this would be a great question for an actual sports psychologist. Are there strategies for doing that? I've read some things where people do try that. We've not done any experiments in the lab ourselves to do all of that, and I don't know that I've looked for any. I'm not really up on all of the actual literature on, does one strategy work better than the other, or, are elite athletes better at doing this than non-elite athletes? My guess is that people that are more accustomed to experiencing kind of moderate to high levels of pain and being able to continue doing things have a strategy that is more beneficial, whatever it might be, than people that are not as accustomed to all of that. They may catastrophize less or something like that.
All right, we're going to take 2 more questions. So here's the first one. It's a little bit longer too, so bear with me. The question states, with the work you've done using the critical power model, have you done any interval studies looking at different interval prescriptions and pain? For example, as a subject approaches the end of the intervals, pain and VO2 are rising proportionately, and during the recovery bouts, VO2 and pain decrease together, ?
Okay, so that's another really good question. So we have not specifically done anything looking at sort of the ramp up and ramp back down during interval training, or kind of repeated intervals in that particular way. So what this does bring up, though, and some stuff that we are very interested in, there's not a lot of data, but there is a little bit. There's some stuff from, and I'm forgetting the first author, from a group in Australia, that if you exercise train using intervals, if you train doing stuff that is quite painful, can you actually train your pain tolerance, or can you train your pain sensitivity so that basically you're less sensitive to pain over time. And there is a little bit of evidence that if you do that, that intervals may actually be more beneficial than kind of the traditional long, slow stuff at changing pain sensitivity. During the bout, my guess is going to be yes, that you know, pain and VO2 are going to rise in a relatively similar manner. And are they going to fall back down in a relatively similar manner? Probably so, but you're going to, the pain rises based upon the accumulation of metabolites. It's going to rise in conjunction with, with fatigue. And so there may be a little bit of dissociation, especially once you're recovering from those couple kinds of things, or maybe VO2 comes down, or pain comes down more than VO2 comes down.
All right, so the last question that we're going to take for this session is there any method for direct assessment of skeletal muscle afferent activity?
The answer to that is yes, there is a direct method. So you can implant kind of these little needle electrodes in and attempt by doing some of that to measure direct activation of the afferents in that particular way. But again, that carries all of the caveats, much like doing needle EMG and things do, that you're getting signaling from a very, very small number of afferents. Are those afferents going to be representative of the entire afferent pool in and around a muscle? Are those things very sensitive to kind of changes like movement and those kinds of things? But yes, there are some, and there are some people that do really, really good work measuring kind of afferent receptor activation in that way. Its application sort of during a bout of exercise, like during cycling and things, is a little bit methodologically a little bit tricky.
Okay, so thank you again, Dr. Black, for a great presentation and great discussion. We always get a lot of really good questions for our presenters on these brown bag presentations. So we're glad that you're with us today. We also want to thank Dr. Ganio for being with us today as well. We also want to share a little bit of information here at the very end about the Southwest chapter. They held their virtual annual meeting live sessions on October 30th. However, content from that meeting is still available on demand until November 28th. So if you'd like to view the content from the Southwest chapter's meeting, you can find that information at the ACSM.org website. And then also we wanted to reiterate that if you participated in today's presentation, you'll receive a recording of the webinar within about a week. And then finally, if you've missed any of the previous brown bag presentations, you can view those, you can view all of the previous ones on the ACSM.org website. And so with that, we're going to thank Dr. Black and Dr. Ganio for their time today, and we are going to say thank you from the National Center, and goodbye, and everybody have a great weekend.